today's topic of discussion is curves in space, or otherwise the same thing is treated as Serret and Frenet formulae. So what this Serret and Frenet formulae talks about is, suppose if the curve is in space, let us say, just imagine my finger like this. Now this finger, right? So this is a kind of shape it is assuming now. Now this curve, so this is a kind of shape which is a curve provided if this is the plane. So on this plane, this curve is there. Now let us say this curve actually is having this particular shape like this. So two fingers are there now. Now actually if I take this plane, at this point it is taking a turn which is not on the plane. Correct or not? Got it? So in such kind of cases, the curve can travel in a different directions in space. So that's why just imagine a spring. So that spring actually it's not a planar shape. Still it is a line, right? Correct or not? Just imagine the spring, that spring shape which is a helical shape. Now the curvature is there in all the directions. So it's not on the XY plane itself. Correct or not? Understood or not? Were you able to imagine? Yeah. So now actually we are going to discuss about such kind of curves which are in space. Let us say a kind of spring which is a space curve, right? Now in such cases, the problem that comes is in case of two-dimensional curve. So let us say this is x and this is y. Now I take this equation, x square plus y square is equal to a square. So this is x square plus y square is equal to a square. Now in this case, if you notice, the curve is on a plane. That means this curve can be constructed with a radius of r. So this curve can be constructed with a radius of r. Now the radius of curvature at this point is equal to r, and the radius of curvature at this point is also r, and the radius of curvature at this point is also r. Now at all the points actually the radius of curvature is same, and then we are talking about only the radius of curvature, assuming that this curve is in a plane. Suppose if I take parabola, now this parabola also, this can be constructed with different radius. Now if you take this particular turn, this can be constructed with a different radius, and this part of the curve can be constructed with a different radius, and this part of the curve can be constructed with a different radius like this. Now at any instant the curvature is different, hence it can be constructed with a different radius, and this radius value with which you are able to construct that curve is called the radius of curvature at that particular point. Got it or not? Understood? Right? So this is what is the fundamental definition of radius of curvature. Now the problem comes when we are dealing with the three-dimensional curves. What happens in case of a spring? So the spring is changing in the x direction, y direction and z direction, all the directions, right? Now actually when we want to define the curvature, how do you define for a spring? So if it is a parabola, we are defining a curvature like this, the radius that can be constructed. So here also the radius that can be used to construct this curve. For an elliptical shape or a hyperbola shape or any kind of shape you can think of on a plane, it will be constructed with certain radius at that particular curvature. So every point is a curvature. So there actually you are finding out the appropriate radius to construct that piece of the curve. So this piece of the curve here, and this piece of the curve you are constructing with a different radius, and this piece of curve actually you are constructing with a different radius. For a straight line, the radius of curvature is infinite because there is no curvature at all. That means the entire thing you can construct it with a radius of infinite. That means the radius of curvature there is infinite. So like this actually on a plane you can construct any kind of planar shape, but in case of three-dimensional shapes, that is helical spring, so there actually there will be a curvature in the x direction, y direction and z direction also, right? Now actually when we are dealing with such kind of curves, so there is something called Serret and Frenet formula which comes into picture, right? So there actually we will be defining two different kinds of curvatures. One is the curvature, another is the torsion, right? So we have to understand what is a curvature and what is a torsion, and then how we will be constructing this kind of curves, that is the three-dimensional curves, right? So those formulae which are used to construct a three-dimensional curve is called the Serret and Freinet formulae. Got it? Understood? Did you get the basic understanding what we are going to discuss? Now actually, first of all, when we are dealing with a three-dimensional curve, let us say there is a three-dimensional curve like this actually which we are constructing. Now here, at any point, if you notice, there will be a tangential direction to this, and then there will be a normal direction to this. This is the normal, and this is the tangent. And then, being it is a three-dimensional curve, so this can be like this kind of curvature if you take it. So there will be a normal which you can construct to both this tangent and normal. So this direction, that is, this is binormal we call. So perpendicular to both tangent and normal. So there will be one more direction which is perpendicular to both tangent and normal. This comes into picture only in case of three-dimensional curves, right? So in two-dimensional curves, actually, this kind of situation is not there, right? Got it or not? Right? So here actually, these three unit vectors, so this is the normal vector, this is the tangential vector, this is the binormal vector. Now, a three-dimensional curve actually, it is always constructed with three different parameters here: normal, tangent, and binormal, right? That means if you take a three-dimensional curve, then you can think of a kind of trihedral which is moving in the curve path. Let me draw that. So that is, so at one point actually, if you can find out a three-dimensional shape. So let us say this is the curve point, and then, so this is the curve, and then this is the normal. This is the tangent. This is the binormal. Like this. Yeah. So this is the curve point. So at this point actually I have drawn a tangent like this, I have drawn a normal like this, and I have drawn a binormal like this. Now actually if you notice, this is the curve actually which is moving in the space. So at this point, here the plane that is containing both normal and tangent, right? Tangent and normal, we call this as osculating plane. Tangent and normal. So the plane that contains both the normals, that is binormal and normal, is called normal plane. And then this one which contains binormal and tangent is called rectifying plane. Right? So this is what is called the rectifying plane. Now, if you can think of a space curve like this, so just identify this particular point which is moving. Now this is like a trihedral moving like this. Correct or not? Imagine, so Rubik's cube. So imagine the Rubik's cube. In the Rubik's cube, all the corners, so one corner if you take it, all the sides, right, edges actually you can think of tangent, normal and binormal. So where this Rubik's cube, this is the bottom, let us say, this is the normal and this is the binormal. The bottom plane we call as the normal plane, and which is containing the tangential plane, so that is tangent and normal, we call this as the oscillating plane, and which contains the plane binormal and tangent, we call as the rectifying plane. Now touch the edge of or the corner of the Rubik's cube on a 3D curve, and then try to trace that curve as if like the tangent is one of the edge. So is along the line of the curve. So that is, if this is the curve, then actually try to identify this particular point which is along the tangent. Then try to trace this Rubik's cube along this particular curve. Now, if you trace that way, you can imagine that how this particular edges, this edge, and this edge are going to change as and when you are tracing that particular curve. That means a trihedral moving in a specific direction. So it will be like a kind of rotation and going like this way, right? So everywhere the direction of the tangent, normal and binormal is completely different. Got it or not? Understood? So now actually how these are changing, that depends on the curvature of that particular curve. Now there are two different curvatures here. One is how this tangential plane is changing, or how this tangent is getting changed, and how this binormal is getting changed. So if you trace only two, that is sufficient enough, so that actually you can imagine how this third vector is getting changed. So that is, if you trace the tangent variation and the binormal variation, you will be automatically trace the normal variation, because we know that all the three are perpendicular to each other. Now the rate of, or the arc rate of change of tangent vector is called curvature. And the second one is the arc rate of change of binormal is called torsion. So these are the two fundamental definitions, curvature and torsion. So the way it is related to the radius of curvature and the radius of torsion is, so this is usually represented with K, and this is usually represented with a letter called tau, and then radius of curvature is given as 1 by K and radius of torsion is given as 1 by tau. So here actually this radius of curvature is which we are going to use in case of tracing a planar curve. Suppose if you want to trace a parabola, so the radius of curvature is sufficient enough to trace the entire parabola, right? And then the radius of torsion for a planar curve is always infinite because it's a plane. So the curvature value is, so depends only for the xy plane, and this is when there is a third plane that is coming, that is z axis also comes into picture, then the radius of torsion will come into picture, because the curvature is on all the three different directions. So normal, binormal and tangential directions. Got it? Still actually we need only two different radii to trace the curve. We don't need the third one, because these two will decide this direction also. Got it? Because we know that the fact that tangent, normal and binormal are perpendicular to each other. Clear? Understood? Yeah. So now actually based on this understanding, we calculate the radii. So we will be calculating the Serret and Freinet formulae based on this understanding. Now let us see how it is going to be. Let T be the unit normal vector, or sorry, unit tangent vector in the direction of the tangent. In the direction of the tangent. Then, so being it is a unit vector, obviously the modulus of t is equal to 1. Right? It's a tangent vector. Now, t dot t is nothing but modulus of t whole square. Now, if you take the derivative of this, so t into dt by ds, and then again plus t into dt by ds is coming out to be 0, because mod t is equal to 1. So this is equal to 1. So this is a constant vector. So t dot dt by ds value will be 0, which implies that t and dt by ds are perpendicular to each other. So we have proved this vector result earlier. If the magnitude of the vector is constant, then t and dt by d, so dt by ds, or any value if you take it, the derivative value, so both will always be perpendicular to each other as and when the magnitude of the vector is constant, right? This is one such case where t is a unit vector means, so t is having a magnitude of 1 which is constant. Now what is this s value? So in case of curve in space, suppose let us say there is a curve in the space, let us say this is the curve, and then this curve, let us say this is the position vector r of t. Now we are talking about the movement of the particle in 3D space. Now if this is r of t, then if there is a change in the value of r, so let us say this is the change in the value of r. So this value is the radial change dr. I'll just read it. So let us draw a curve in a space. Now let us say this is the curve in space. Now this is one position. This is r of t. Now this r is changed after certain time to a different value. Now the radial change is this part. So this is dr. And corresponding arc also is getting changed. So this value, the actual change in the arc value is ds. So arc length actually we consider, let us say this is S0 where we have started the analysis, and at a distance of S actually there is a change of ds. So S is nothing but the arc length. Now if you take the derivative with respect to the arc length when we are moving along the curve, so this is the tangential direction. So when you are moving from here to here in the tangential direction, now we have taken the derivative of the tangential curve with respect to that arc length ds. So and then it is proved to be t dot dt by ds is coming out to be 0, and then t and dt by ds are perpendicular to each other. Got it or not? Understood? So let us say, so these two are perpendicular to each other, then so let us define a unit vector in the direction of dt by ds, and let it be n. So because these two are perpendicular to each other, I call this particular direction as the normal direction. So then dt by ds value is nothing but some constant k into n, because dt by ds direction and n direction are one and the same, where n is the unit normal vector. Got it? Note down till this point. Then, so we have got this relation. We have defined a tangent vector, and the dt by ds value is coming out to be kn. So where n is the unit normal vector. And then let us define one more vector. So n be the unit normal vector. So let us define B equal to T cross N. T cross N. So being T and N are unit vectors, hence B will be a unit normal vector. B will be a unit vector which is perpendicular to both tangent and normal. So So this is perpendicular to both tangent and normal, right? Obviously, right? So here actually we started with the tangent, and then the derivative of the tangent with respect to the curve is dt by ds is coming out to be the normal direction. Then, so if you select t cross n, then obviously there will be a unit vector which is coming out perpendicular to both t and n, because this is a cross product, right? Cross product will always result into a vector which is perpendicular to both the vectors. Hence, B is coming out to be t cross n. And then this is defined as, so this B vector is termed as binormal, right? Therefore, tangent T, normal and binormal. B are perpendicular to each other. Are perpendicular to each other. So this is the fundamental understanding. And then we have got the one relation, that is dt by ds is coming out to be k times of n. This is one of the Serret and Frenet formulae. Total there are three different formulas are there. So dt by ds value, dn by ds value, dv by ds value. All the three together we call as Serret and Frenet formulae. So these three values will give the variation of the tangent vector, normal vector and binormal vector when you have a minor displacement from the curve. So that is when you are moving on the curve, right? So if there is a change in the value of the perimeter S, so you are going to get a variation in the value of tangent, normal and binormal. So these value dt by ds and dv by ds and dn by ds value will show the relation of how this curve is moving when there is a change in the value of S. So those three formulae we call as the Serret and Frenet formulae. Got it? In that, one of the formulae is this one. Now actually we calculate other dB by ds value we calculate. From there you calculate dn by ds. Now for that, what we will do is, because dt by ds is equal to k dot n, then let us consider, so B is a unit vector. Hence, dB by ds dot B is again 0. That means these two are perpendicular to each other, obviously, right? Because the dot product is 0. Why dot product is 0 is B is a unit vector, which is nothing but a constant magnitude vector. So therefore, B and dB by ds are perpendicular. This is one understanding. And then let us consider T dot B. So obviously dot product of T dot B will be 0 because these two are perpendicular to each other, tangent and binormal. So obviously tangent and binormal will have 90 degrees angle in between them. So if you take the derivative of this, so dt by ds dot B plus B dot T dot dB by ds is again equal to 0. Got it? And then dB by ds value. Okay, so you note down till this point. I am going to erase it and write it. Now actually from this relation, so from the derivative of P dot B dt by ds dot B plus T dot dB by ds. So this is coming out to be 0. And then dt by ds value is nothing but kn. So this is kn dot B plus T dot dB by ds equal to 0. Now being n and b are normal to each other, being n and b are normal to each other, hence n dot b is equal to 0. So if n dot b is equal to 0, then equation number 1 will become, so T dot dB by ds equal to 0. Obviously, right? So here dB by ds dot b equal to 0, dB by ds dot t is equal to 0, right? So with respect to t, dot product is 0. With respect to b, dot product is again 0. Hence, what should be the direction of dB by ds? Normal to what? dB, yeah, obviously n direction, exactly, right? So it is perpendicular, yeah. So it is perpendicular both t and b. So hence, dB by ds is perpendicular to both b and t. So I call this as dB by ds is equal to, I call this as minus tau n. So why we treat this minus as, so this is actually the standard convention. For a positive value of tau, so you will take the opposite direction of the normal. So here the tangent direction and normal direction. We are concluding this tangent and normal direction based on the dot product of t dot dB by ds and b dot dB by ds. Now actually, ideally, the way we conclude this is, it may be normal in the normal direction or maybe in the opposite to normal direction also, right? Or to be specific, parallel to n vector. Got it or not? Understood or not? It will be parallel to, yeah, parallel to n vector. So that's why we can treat this dB by ds as minus tau n. So this is the standard convention. So in the negative direction of n, actually we take this as dB by ds value. So that's why it is minus. So this is formula number 1 and this is formula number 2. So this is tau. So tau is called as torsion. This is called as torsion. And here K is called as the curvature. K is called as the curvature. So note down till this point. Now actually we are going to discuss, that is dN by ds value also based on these two. So dt by ds is equal to Kn and dB by ds is equal to minus tau n. So this is another formula. And the third one is, let us consider n is equal to b cross t. So n is equal to b cross t. Now, if you take the derivative with respect to s, dn by ds, so this is b cross dt by ds plus dB by ds cross t. So this is the cross product derivative. Now b cross, here dt by ds you can replace as Kn and then plus dB by ds you can replace as minus tau n cross t. So this is K times of b cross n minus tau n cross t. Now here, so tangent, normal and binormal, this is the order we follow. So t cross n is b and n cross b is t. So here b cross n is nothing but minus t. So k into minus t and then minus tau into, so n cross t. So this is minus b. This is tau b minus kt. So this is dn by ds. This is the third formula. So all the formulas together, all the three formulae together we call as Serret and Freinet formula. Got it? And K is called curvature and tau is called torsion. And 1 by K is radius of curvature and 1 by tau is radius of torsion. Got it? So this is how we define the radius of curvature and radius of torsion. These are applicable if there are curves that are moving in a space. Got it? Any questions on this? So actually in the examination, the problems that are going to be asked from this particular section, so with the application of Serret and Freinet formulae, so he will be asking us to find out the radius of curvature and the radius of torsion values. Now one more important relation, we started with the discussion of the direction of, right, the tangent direction. So this is the tangent direction, right? So in the tangent direction we call this as t. So this t value we find out so based on dr by dt. So if this is the position vector, then this is r of t. So dr by dt, so this is velocity vector. So velocity, obviously it will be in the direction of the tangent to the, it will be in the direction of the tangent. How we conclude that is, this is dr by dt, what we do is dr by ds. So rather than that, right, so this will be considered in a different manner. That is, first we consider ds by dt. So ds by dt is nothing but, suppose if the particle is moving along this particular line, so let us consider the s value here. From this, actually if there is a change of ds, then that ds value with respect to time, this is the velocity in the direction of perimeter. So when the curve is moving along the perimeter line, so that is, if the particle is moving in this particular path, then the velocity on this particular line is ds by dt. Now this ds by dt is getting multiplied by dr or delta r to be specific, and delta r divided by dt. We will be multiplying and dividing with delta r. So why we are doing this way is, so this part ds by dr, if you consider the change in the value of r, so this distance is the change in the value of r, dr, and this arc length, so this arc length is ds. Now if you take the ratio of ds by dr as t tending to 0, this will be almost close to this one, right? So this ratio as t tending to 0, ds by delta r value will be obviously equal to 1, right? Yes or no? Right? Because this is the arc length, this is the radius change. These two together will be almost closing one on top of the other. So, and it is equal to the one another as and when the t value tending to 0. That means the change is treated almost 0. Then the ratio of the arc to the chord will be, so this is arc by chord. So obviously these two are equal, hence this will be 1. So this part ds by dr value is coming out to be 1 as limit delta as t tending to 0. So in this case, this can be treated as dr by dt mod. So this is equal to ds by dt. So this formula actually, when we apply Serret and Freinet formula, this S value we will be finding out first, because we wanted to calculate with respect to S, dt by ds, dr by ds, and so dt by ds, dn by ds, and db by ds we are calculating. When we are taking the derivative with respect to S, S value how we are going to find out is based on this principle. So this ds by dt value is equal to dr by dt value, which is nothing but the velocity magnitude. So if you want to find out S value, so this is ds is equal to dr by dt mod dt. So this integration we will be using, so to find out integral, so t naught to t dr by dt mod dt. So this S value we are going to use to find out the derivatives with respect to S. Got it? So you have to remember this. Understood? Any questions on this? So the application is to trace any particular space curve, right? So any space curve actually, so we are trying to trace it. So here actually when you want to construct a space curve, you have to be aware of the radius of curvature and you have to be aware of the torsion, right? So the radius of torsion. So these two values actually will decide to trace the real curves, right? So that's where actually we are going to use it. Now the real practical application of this is when a particle is moving in a plane. So when a particle is moving in a space, then the methodology that we are going to adopt to find out the path of that particular particle, these are the things actually that we are going to use it. Got it? Understood, Deepak? So particles that are moving in a 3D space. Let us say in the nuclear experiments, right? So how an electron is moving or a proton is moving in the presence of electric field or the magnetic field. So there actually, if you want to identify the path of the particle, how it is going to move. So these are the things actually which we are going to use it there. Clear? Okay. So this is about the Serret and Freinet formulae. So I will be taking the problems in the next class based on Serret and Freinet formulae. Yeah. So till then, yeah, good night. Yeah, thank you. Bye.